Welcome to the Picture Language Seminar. It's a great pleasure today to have Jesse Peterson. Jesse is an expert on phenomenal algebras. He was a student of Søren Poppa, postdoc with Vaughan Jones, and now is on the faculty at Vanderbilt. We're looking forward very much to hear your talk about amenability. That's a big topic and very interesting. So, Jesse, you can share your screen and tell us all about it.
All right, thank you. Let me go ahead and share. Oh, that's the wrong thing to share. Let's try this again. Share it. There we go. Here we go. Everyone can see that all right?
Yes, perfect.
Okay, so thank you very much for allowing me to speak here and tell you a little bit about amenability and von Neumann algebras and some of my contributions in this area. So I won't assume that any of you know too much about von Neumann algebras, so I'll try to keep this more like a survey talk rather than a technical talk, but I'll still try to give maybe a flavor of some of the proofs. So to begin with, let me talk about maybe the origin of amenability, and that's the Banach-Tarski paradox. Which was about 100 years ago. Their paper was published in 1924. So it's been about 100 years since they did this. And what they proved is that if you take the uniball in 3 space, and then you can split this uniball into finitely many pieces. So we can write this ball here, and we can write it as a union of finitely many pieces, say A1 through AN. And then you can, for each one of these finitely many pieces, you can apply Euclidean transformation. So just rotation, shift, reflection, etc. And then from that, you can rearrange, after applying the Euclidean transformation, a different one to each piece. You can arrange it so that you get 2 uniballs. So this is then, this new thing is the union, as I goes from 1 to n, of some gamma I AI, where gamma i's are Euclidean motions. And this is, very paradoxical because, of course, intuitively you think that Euclidean motions should preserve volume, and yet here we have, we seem to be creating matter out of nowhere, which is pretty remarkable. As far as I know, nobody has been able to apply this to real world situations. Of course, the difficulty is that we know, of course, that if we have, say, Lebesgue measure, then Euclidean transformations preserve Lebesgue measure. So therefore, these pieces that we have to break things into have to be very non-measurable. So this is hard maybe to do in the real world situation, as far as I know. But anyway, von Neumann was very much interested in this, and von Neumann has his own version of this paradox. So this is from 1929, where he noticed that in 2 dimensions, you could try to do the same thing, and you're met with limited success. Specifically, if you allow for something more general than Euclidean transformations, but still volume preserving, then this is still possible. So in 2D, this also works for the, say, unit disk instead of the uniball. With transformations, from volume preserving transformations. So you can take scaling transformations, and then you can also apply elements of SL2R. And then you still get this sort of paradoxical decomposition but it fails with Euclidean transformations. So it's impossible to take the unit disk and then split it into finitely many pieces and then rearrange it with Euclidean transformations to get 2 unit disk. And the reason this fails, and this is what von Neumann discovered, is that, so here if we take R2 cross SO2, so this group is amenable. And this is where he introduced this terminology of amenability and this notion of amenability. Specifically, if this is called this group gamma, so there exists a state, let's call it phi, from gamma to, or from L infinity of gamma to the complex numbers. So a state that takes positive functions to positive numbers that is left invariant, is invariant under left translation. So the group gamma acts on L infinity, acts on itself on the left. And so then you get this dual action on L infinity on functions. And this state is left invariant. And the existence of this state is not so difficult to construct. If you can do it for abelian groups, then extending it to the solvable groups is not so difficult. But on the other hand, this group down here, this R2 cross SL2R, or also the group that Banach and Tarski were considering of Euclidean motions in 3 space, they contain a free group, and a free group is non-amenable. So on the other hand, we have F2, which is the free group on 2 generators, is not amenable. Meaning it's not possible to produce such a state. So let me maybe give a brief argument about why this is not possible for a free group. So here I'll copy over the right-hand side so that we still have it on the screen. So to do that, let me draw a picture of the free group. So this is the Cayley graph of the free group. So it's going to be a tree. You can imagine this keeps going. I have to draw my my edges smaller and smaller so that they fit in the plane. And each vertex on this tree represents an element of the free group. So the vertex in the middle, this is the identity element. Going to the left or going to the right, this starts, this is our element A. Or if we went up, this would be my element B. And then at each point, you multiply on the left by A or B or A inverse or B inverse. So this would be B inverse down here. And so from this, you associate to each vertex on this tree a unique word, which is in reduced form. And so that gives you an element in the free group. So we identify the free group with vertices of this tree. And then there's a natural set that we can consider in here, mainly this set right here. Let's call this A. So these are all words that start with A. Writing from the left to the right. And then you can imagine on the left-hand side, we have A inverse. On the bottom, we have B inverse. And on the top, we have B, all the words that start with B. And then the thing to notice here is what happens if we take A, this set A, all the words that start with A, and we multiply it by A inverse. And then a moment's thought, you realize that this is nothing but this set right here, which is all words that don't start with A inverse. So this is just F2 take away this A minus, all the words that start with A inverse, and these are equal. All right, because any word that doesn't start with an A inverse, you can write it as something starting with an A and then multiply by A inverse to get to that. And so what this means is that if B is an invariant state, so then we can apply it to the characteristic function on F2, take away all words that start with A inverse. And since this is just A inverse times A, this will be the same as the characteristic function on A by left invariant. But this means that the set that's left over, so therefore, in particular, the characteristic function of all the words starting with B, or the characteristic function of all the words starting with B inverse, or the characteristic function of the identity element. So this has to be 0 because it's between these two things. We add this function to this function and we get this. But now you can imagine if you replace the roles of A and B for the same reason, we also get that phi applied to characteristic function of A, and also the phi applied to the characteristic function of all the words starting with A inverse. This also has to be 0. But this is then a contradiction. We've shown that the entire space has measure 0, which is a contradiction. So this is why free group F2 is not an amenable group. And this was really this has spurred a lot of interest, and there's still research going on in this area.
Okay, but Jesse, can I just make a comment?
Of course.
My understanding is that even though von Neumann almost invented amenability for groups, the property of amenability for groups did not enter into their analysis of von Neumann algebras whatsoever. That wasn't.
That's right. That's right. So now, so let me talk about von Neumann algebras, which were also developed by von Neumann almost at the same time as he developed amenability. However, as George points out, initially, there was no connection, and in Murray and von Neumann's development of von Neumann algebras, they don't mention amenability anywhere, as far as I'm aware. Is that your comment, George?
Yeah. Oh, yes, exactly. So I was just a little puzzled why you were starting off with it. I'm sorry.
Well, I'm starting out with Banach-Tarski is a very pleasant, nice picture to start off with.
Yeah, right. So, but I guess what von Murray and von Neumann, the property of the free group, that they were the way they translated Banach-Tarski was with non-property gamma.
That's right. That's right. So yeah. I'll mention that in just a moment.
Okay. I'm offending. Sorry.
You're doing fine. So yeah, let me. So now let me switch gears a little bit, and I want to talk about a different development of von Neumann right about the same time as he developed this. So this was his theory of von Neumann algebras. So this is von Neumann algebras. And the first paper was in 1930, so just a year after he did his work on amenability. He introduced this notion, but it really wasn't developed until a series of papers in the late 30s and early to mid 40s by Murray and von Neumann. But let me first give the definition. So a von Neumann algebra is a star subalgebra let me give it a name, say M, of bounded operators on a Hilbert space, such that it contains the identity element and is closed in the topology of pointwise convergence. In other words, if you have a sequence ti converging to t. So this is if, when you apply them to a vector, they converge to the corresponding vector. So this is called the strong operator topology, for those who've seen it before. So this is the definition of a von Neumann algebra. And a very famous theorem of von Neumann from this paper is that we could replace this condition is closed in the topology of pointwise convergence. We can replace this with is equal to its own, the commutant of its commutant. So it's equal to its bicommutant. So M is equal to its bicommutant. And this is where the commutant of any set is defined to be the set of operators that commute with everything in that set. So one inclusion here is obvious. It's obvious that M is included into its bicommutant. That's for any star subalgebra, unital star subalgebra. And von Neumann showed that this is the same as the closure in the strong operator topology, or also the weak operator topology. So examples of this are if you have X mu, say, a probability space. So then you can consider L infinity of X mu and view it as sitting inside of bounded operators on L2 of X mu. And this is by pointwise multiplication. So if you have an L infinity function, you multiply pointwise by an L2 function, you get another L2 function, and the norm is of this operator is bounded by the L infinity norm. And it's a fun exercise, a good exercise, that you can check that for this algebra, this L infinity, it's actually equal to its own commutant. So if you have any operator that commutes with any of these L infinity functions, then it's already itself an L infinity function. And what this means is that in particular, it's also equal to its double commutant, and hence is a von Neumann algebra. Another example of a von Neumann algebra is, and this is due to Murray and von Neumann in 1946, is if we have gamma a group, and then we can consider the left regular representation of gamma on little L2 of gamma. And this is given by convolution, if you like. So lambda t of f is just take the Dirac function of t and convolve with f. Or if you like, you just extend the group operation on the group itself. You extend that to L2, and that gives you the left regular representation. And then they consider the group von Neumann algebra is just the von Neumann algebra generated by this representation. So T gamma, and then you take the bicommutant of that. So this is the group von Neumann algebra. Why were they interested in this von Neumann algebra? Well, it's useful to think of what happens when gamma is abelian. So when gamma is abelian, we have the Fourier transform, which takes L2 functions on gamma to L2 functions on the dual group, which is a nice compact abelian group. So this should be a big L2, excuse me. This should be a big L2 with a Haar measure on the compact group. And then it's again a fun exercise to see that if we take this unitary given by the Fourier transform and we conjugate this unitary, that this gives an isomorphism between L infinity of the dual group and L of the group. So this is when gamma is abelian. And so because of this, you can think of the von Neumann algebra, the group von Neumann algebra in some sense as L infinity of the dual group. But in the non-abelian case, you know, this doesn't really make sense in an obvious way to say what we mean by L infinity of a dual group, but we can still make sense of this von Neumann algebra in this way right here. Yeah, so let me say in particular, so note that if we have gamma and lambda, infinite abelian groups, countable, all my groups will be countable, infinite abelian groups. So then we get right away that their group von Neumann algebras are isomorphic. Because von Neumann showed, in fact, that any two probability spaces without atoms, their L infinity spaces are isomorphic as algebras. So in particular, this is an example here. So this is a particularly nice class of von Neumann algebras because they also have a nice property. They have a trace. So let me define what the trace is. So we also have a trace on these von Neumann algebras, which is given by just you take the x, you apply it to the Dirac operator at the identity, and then you take the inner product with the Dirac operator at the identity. So this is a positive linear functional. That's easy to see. It's given by this vector state, and it satisfies the very nice property that this is a trace. So specifically, i.e. that tau of xy is equal to tau of yx, and this is for all x and y in the group von Neumann algebra. So just like with the n by n matrices, we have this nice trace there. For group von Neumann algebras, we have a nice trace also, except these are infinite dimensional. And this is exactly the Haar integral if you're in the abelian case here. So you see that this is a trace. This is also another good exercise. You can check when x is the group element, x and y are both group elements. So they're given by 2 lambda t and lambda s. And here then it's easy to see this, and then you can expand linearity linearly and use continuity to pass to the whole von Neumann algebra to get this formula for the whole von Neumann algebra. So this is the group von Neumann algebra. And then as George mentioned, so Murray and von Neumann, I already mentioned in the abelian case, this is abelian, but one thing they did is they also showed the extreme opposite. So this is also Murray and von Neumann. They showed that L gamma is a factor, meaning that the center of the algebra is just the scalars. And this is if and only if the group gamma has infinite conjugacy class. So ICC, except of course the trivial element will have its own conjugacy class, but every non-trivial element, the conjugacy class should be infinite. So these are ICC groups, and these exactly give factors. So this is the extreme opposite of the abelian case. So for example, free groups are ICC, that's easy to see. And another, so example, free groups. And another example is, say, the infinite symmetric group of finite permutations on the natural numbers. This is also not difficult to see that this is ICC. And Murray and von Neumann showed, in fact, that these two von Neumann algebras are, in fact, not isomorphic. And this was the first example here where we have infinite dimensional tracial factors, which are non-isomorphic. So this is really, I think, kind of the beginning. So this is in their 46 paper. And this is really the beginning of the theory of von Neumann algebras. So maybe before then it was kind of nice tools and development, and there was a more general theory, but this shows that there's a lot of interesting structure going on here. Now, the way they prove this, they introduced something called property gamma, but there was a different proof given later, which is due to Jacob Schwartz, where in fact he showed something stronger. He showed that if two groups have isomorphic von Neumann algebras, so then gamma is amenable if and only if lambda is amenable. So in fact, and this I think is quite remarkable, because von Neumann developed the theory of amenability, and almost at the exact same time he developed the theory of von Neumann algebras, and he was very interested in knowing about properties of von Neumann algebras, and it turns out that amenability is kind of naturally embedded into the theory of von Neumann algebras through this result of Schwartz, and this was very unexpected. I don't think, well, I don't know what von Neumann foresaw at that point, but to me this is quite surprising. And the idea of the proof, so what's the proof? I won't go into details, but let me at least give an idea. So the idea of the proof is that we have this copy of L gamma, which sits inside of bounded operators on L2 of gamma. And then we also have another natural von Neumann algebra inside there, and that's L infinity of gamma sitting inside here. Again, just as pointwise multiplication. So this is kind of the abelian case here, and this is the kind of the dual case here. So it's in a sense, we have L infinities of both the group and the dual group that sit inside, and they sit inside in kind of a natural orthogonal way. And you can play between these two von Neumann algebras in a nice way. So specifically, using these two decompositions, you can transfer between states on L infinity of gamma and states on B of L2 of gamma. Let me give this one a name, phi, such that phi restricted to L gamma is the trace. Let me call this phi. And there's a natural way to go back and forth between these two worlds. One to go from states to states on B of L2. We have a natural conditional expectation from bounded operators to this diagonal subalgebra. So if you like, this is just compression to the diagonal subalgebras. If you think of these as matrices, this is just restrict to the diagonal entries. And that's exactly this conditional expectation. And then we can compose it with this phi, and we get a state here, which is the trace. And you can also go back just by restriction, viewing L infinity inside there. And using this, you can then see, so this wasn't Schwartz's original proof, this is a simplification due to Alan Kahn, is you can show that left invariance for phi exactly corresponds to what Alan Kahn called a hypertrace for L gamma. So meaning that C, not only is this a trace when you restrict it to L gamma, but it still satisfies this traciality property for X and L gamma, and T now can be any bounded operator. And you can go back and forth. Given a hypertrace, you get this left invariant state, and given as left invariant state, you can construct this hypertrace in this way. And so you can see that amenability is is exactly realized in the framework of von Neumann algebras in this way. All right, so what does yeah, so then this was extended, and I want to mention also the amazing work of Connes in his 76 paper. And in his 76 paper, he actually showed, he completely classified amenable von Neumann algebras. Well, modulo some type 3 setting, which Haagerup helped with in general. So there was Connes in 76. This was most of the work. And then there was Connes using these works and together with Haagerup, who finished up a final case. So they completely classified amenable von Neumann algebras. And I'm going to be a bit vague here. So one thing, I haven't actually defined amenable von Neumann algebras, but if you're in the tracial setting, you can take this as a definition, the existence of a hypertrace. So this is, you can take this as a definition of amenability for tracial von Neumann algebras. For the non-tracial case, you have to generalize this, and there's a notion of injective von Neumann algebras. And Alan Connes showed that injectivity is the same as being a union of a limit of a union of finite dimensional von Neumann algebras. And from this, you can really do a lot of work in the classification. I'm also being a bit vague on what I mean by completely classified. So I mean, there are certain invariants, but in the type 3-1 case in particular, these invariants themselves might be difficult to classify, if you can call that. But they at least.
May I just make another quick comment?
Please do, yes.
It seems to me that, that the work of Krieger ought to be recognized a little more. Namely, the work of Connes and Haagerup, you could express it in a different way. They showed that they characterized axiomatically the von Neumann algebras that had already been classified by Krieger.
Yeah, that's a very good point, George. Thank you for mentioning that. So yes, what Connes and Haagerup did is they essentially, in the type 3 setting, they reduced the classification of von Neumann algebras to exactly the classification of cross products where Krieger had already done his work with flows and stuff like that. So that's a good point. Maybe I'll also mention Krieger there. Thank you for that. All right, so this was the setting of amenable von Neumann algebras, and you could maybe be a little bit discouraged as a survey of looking at this because, well, everything's classified. Maybe that looks too easy, but of course that's the very wrong perspective. Just like with Hilbert spaces, everything is classified very simply, but Hilbert space is very complex and extremely interesting. And that's the perspective I'll take here. But let me also say in the extreme opposite, and I also want to mention this work of on property T. So on the extreme opposite case of amenability, we have property T. So let me tell you that. So another way to phrase amenability is gamma is amenable if and only if the left regular representation has almost invariant vectors. So i.e., there exist Cn and L2 of gamma univectors such that they become more and more invariant under each T. So this is equivalent to the group being amenable. It's not obvious that this is equivalent, but it is. And there's an extreme kind of opposite end of this due to Kazhdan. So this is from 67, where he defined that gamma has property T if whenever you have almost invariant vectors, that implies that you have actual invariant vectors. If having almost invariant vectors and this is for any unitary representation, implies we have a non-zero invariant vector. So that's the definition due to Kazhdan. So his main interest in this is that there's two things you can see right away from property T. One is that you can see that if you have property T, then you have finite abelianization because property T passes to quotients. And of course, infinite abelian groups don't have property T because they're amenable. Any infinite amenable group cannot have property T. And the other thing he was interested in is property T implies finitely generated, which is another easy exercise to see. And then he also showed that property T passes to lattices, and he showed that for higher rank simple Lie groups, they all have property T. Well, at least he showed for rank 3 or higher, and this was extended to rank 2 or higher. So for example, if gamma in G is a lattice in a higher rank, so for me, that's rank greater than or equal to 2, simple Lie group. And based on, so then in the 80s, so 1980, here we have Connes and Jones. So they showed just like amenability, property T is also something that can be encoded in the von Neumann algebra. So if we have L gamma is isomorphic to L lambda, so then gamma has T if and only if lambda does. So again, somehow this property T is kind of the absence of amenability for any representation, and we see that this is closely connected to the von Neumann algebras. Based on this, Alan Kahn conjectured so this is Kahn in the 80s. That you should be able to see some of this rigidity from the higher rank situation. We should be able to see this in the von Neumann algebras, which is a bit surprising because Alan Kahn showed that, you know, all part of this classification, all tracial factors, infinite dimensional tracial factors are isomorphic if they're amenable. So somehow in the non-amenability, he conjectured there should be lots of rigidity coming from the higher rank. So specifically, he conjectured the following thing. So suppose gamma in G is a higher rank lattice. In a simple Lie group. Well, lattice in a higher rank simple Lie group, I should say. And let's suppose we have a homomorphism from gamma to the unitary group of M, where M is a tracial factor. And let's suppose that we assume that the range of this is not precompact. in the SOT. And we'll assume that the range generates the von Neumann algebra. Otherwise, we could look in a von Neumann subalgebra. So then the conclusion is that pi should extend to an isomorphism of the von Neumann algebras. So where did Alan Connes, so that's the conjecture, that the rigidity of the lattice should somehow say that from the image of this homomorphism, we can already recapture the von Neumann algebra. So where did this conjecture come from? Well, if you replace a few things here, so specifically if instead of replacing the unitary group of the von Neumann algebra, you replace this with, say, H, a simple Lie group. And now, instead of this condition here, that it generates the von Neumann algebra, if you replace it with the image as Zariski dense, and now if instead of extends to an isomorphism of the group von Neumann algebra, you say it extends to an isomorphism or a homomorphism of the groups. So then this is exactly Margulis's superrigidity theorem. So this here is Margulis superrigidity. And so he viewed this as, there should be this phenomenon of Margulis superrigidity in the von Neumann algebra setting, and there were two conjectures he made. There's this conjecture, so this is called the operator algebra superrigidity conjecture. So this is the OA superrigidity. And then there's another conjecture he made, which was called property T superrigidity, which is still open to this day. But this conjecture he looked at, and it's quite a bold conjecture because at the time there was not a single example of a group or a lattice gamma and G for which this was known to be true. And in fact, it wasn't until Becca in 2006 that this was shown to be true for gamma to be PSLN Z n greater than or equal to 3. And Becca's proof was unfortunately extremely ad hoc. In particular, he used congruent subgroup property. He used lots of very high-level techniques to actually prove this. So there was, I think very little hope of that Becca's proof would extend to the general von Neumann algebra case. But fortunately, I was able, so this is myself in 2015, that this is in fact the conjecture holds in general. So Connes. And what does this have to do with amenability? So I've done all this, most of this talk so far talking about amenability, and what does this have to do with it? And to understand that, you have to know another proof of Margulis, and that's Margulis's normal subgroup theorem. Which states the following. So if we have gamma, again, a lattice in a higher rank simple Lie group, with, say, trivial center. And now if we have a normal subgroup of this lattice, So then in fact, there aren't so many normal subgroups. So what he showed is that then either sigma is the trivial group or its finite index. And his strategy for proving this, so here's again the proof idea. His strategy for proving this is quite remarkable. He supposes that the subgroup is not the trivial group. And then he shows that the quotient group is amenable. Well, so therefore the quotient group is amenable, but then we also have Kazhdan's work, which showed that the group gamma has property T, and hence the quotient group also has property T. So by Kazhdan, the quotient group also has T. And amenable says the left regular representation has almost invariant vectors. Property T says that it has invariant vectors. And if the left regular representation has invariant vectors, that's easy to see that that implies finite. So it's quite remarkable that this strategy actually works. And how is this connected to operator algebraic superrigidity? Well, let me just notice. So if, I didn't copy over. So if we consider this representation here from gamma to the unitary group of the von Neumann algebra of the quotient group, so then this is a setting of operator algebraic superrigidity. So the image is not pre-compact unless the quotient group is finite. So we get either the quotient group is finite. So if pi of gamma is pre-compact, or we get that it extends to the von Neumann algebra. Pi gives an isomorphism of the von Neumann algebra. But then, of course, we have to have sigmas to trivial. So operator algebraic superrigidity actually implies Margulis's normal subgroup theorem. And so the idea around proving operator algebraic superrigidity is to use ideas in Margulis's normal subgroup theorem. Let me mention one other corollary of operator algebraic superrigidity. So here's another example. And let's suppose that again, gamma in G is a higher rank lattice. And now let's suppose that we have an action, which is probability measure preserving and ergodic. Well, in this case, there's also a natural von Neumann algebra, which you can associate to any PMP ergodic action. This was introduced by Feldman and Moore. So whenever you have a PMP ergodic action, you get an equivalence relation, which is coming from the orbits of this action. So the equivalence relation, this is just going to be the set of all pairs, x and gamma x, such that x is an x and gamma is a gamma. And from this equivalence relation, you can construct a von Neumann algebra. If you think of this, this is an equivalence relation as a groupoid. So you can imagine that there's some sort of generalization of the group von Neumann algebra construction. And that's exactly what Feldman and Moore did. So they showed that here we have a tracial von Neumann algebra. which will be a factor. Factor comes from ergodicity. And so now we have again this representation of our group into the unitary group of this von Neumann algebra. Now it doesn't necessarily generate this in general. That's an interesting question when it does, which was studied by Vershik. But you can still apply operator algebraic superrigidity to the range, the von Neumann algebra generated by the range. And so from this, you can get, so operator algebraic superrigidity implies again a dichotomy. So either X is a finite set, essentially, or the action is free. So this is a nice consequence of operator algebraic superrigidity, that every action, every PMP ergodic action on a probability space without atoms is automatically a free action. So this is also not my theorem. So I should mention that this is another famous theorem, which is due to Stuck and Zimmer. Which is from, I think, 94. So this free actions for our higher rank lattices. And Stuck and Zimmer, they took their proof. They also borrowed it from Margulis' normal subgroup theorem. And so for operator algebraic superrigidity, I want to give you a flavor of this. It's also coming from the ideas behind the Margulis normal subgroup theorem. So specifically, let me remind you, it's set up here. We have a lattice and a Lie group. G higher rank. We have a representation of this group into a von Neumann algebra, which generates this. And we're assuming that the image of gamma is not precompact. And then we want to conclude that this representation extends to the von Neumann algebra. So what we do is we look at the Poisson boundary of the Lie group. So this is the Poisson boundary. And this, so this is, you can realize this is some space of harmonic functions. For the sake of time, I won't describe this too much, but the remarkable fact of this is that the Poisson boundary is what Zimmer called an amenable action. So this is a Zimmer amenable action. And as a consequence of this amenability coming from the Poisson boundary, we get a natural amenable von Neumann algebra. So I'll describe that here. So if we take all functions, which are L infinity functions from the Poisson boundary, but now we let them take values in B of L2 of M. And we have a natural gamma action there, and we look at equivariant functions. And when we look at extravariant functions, so this is some von Neumann algebra, and the important thing is that it contains M. And because of Zimmer amenability, this is amenable. And this should be thought of, if you've seen Margulis's proof, or if you're familiar with that at all, this is part of his proof is the so-called factor theorem. And this should be thought of as a non-commutative non-commutative factor. Of course, this is maybe not great terminology because this is factor in a different sense in ergodic theory, not factor in Murray von Neumann algebra sense. But then the point is that there's a non-commutative factor theorem you can prove, and that shows that in fact this M is nothing but this B under the conclusions here. So this follows from a non-commutative factor theorem. And in particular, that implies that M is amenable. And now you can apply Connes and Jones' work using that the gamma itself is property T, and then you also get that M has property T also. But amenability and property T for von Neumann algebras, just like for groups, implies finite dimensional for factors, and so then you get a contradiction from this sense. And then finally, I'll end with just mentioning a follow-up, and that is that this work, so I mentioned everything here for simple Lie groups. So here G is gamma is a lattice in a simple Lie group. So you could also ask the same thing for semi-simple Lie groups. And much has gone on in this direction. In particular, there's work of Boutonnet and Houdet, who've done some really remarkable stuff about this and generalized this operator algebraic superrigidity techniques as well. And then there's also a paper of Uri Bader, Boutonnet, Houdet, and myself, where we've also generalized this to products. There's one case which is still outstanding for the semi-simple case, and that is when you have a lattice, an irreducible lattice, and a product of rank 1 groups. That's where there's still some difficulty there. But anyway, I thank you for your attention, and I'll stop here.
Well, thank you so much, Jesse. That was an absolutely beautiful survey of the field. I think it will be useful for experts and non-experts alike. And so now I'll stop sharing your screen and open up the discussion. For people who want to contribute, please turn on your video so we can see you. George, it looks like you're ready to say something.
Okay, well, I just have a comment which is it's not quite pertinent, but relative to Poisson boundaries. That if it's a Poisson boundary, it's amenable. In fact, every amenable action is a Poisson boundary in a strong sense.
So what do you mean by that, George? Because I'm not
well.
familiar.
There's a paper by Thierry Giordano and me proving, but so a Poisson boundary of a random walk, but a matrix valued random walk.
Okay, yes. Now I remember. Yes.
Okay, yeah. And then but that was for a discrete group, and then for locally compact groups, Scott Adams joined us, and we did that too. But I mean, so it's not at all related to what you say, what you did, but what you're talking about.
Yeah. Thanks. Yeah. I am familiar with that paper. It's a nice paper.
I've even seen that used. I even saw that getting used once. Kajmanovich used it once, I think.
Yeah, I should also mention, so Poisson boundaries, so enter the picture here. You can also define Poisson boundaries abstractly just for von Neumann algebras. And this is something I did with my student Sayan Das. And there are some results that you can get out of that as well.
It was, thank you.
So are there any other comments or questions? Jun.
I have a question. So when you are handling the lattice in hierarchy group, they are pretty, but once you just consider the, so you can also use property to prove some result for the S arithmetic group. But if you just consider a reductive group over a global field, say just rational field, it's also a lattice in the Delic group. And we have no conjugate probability because it's no longer finitely generated. So yeah, the question is still, can we just prove the operator algebra super rigidity? So it's very hard to do the first step, just the extension to any unitary group of Neumann algebras.
Yeah, so I think even the normal subgroup theorem fails in that level of generality, if I'm not mistaken. However, there should be some sort of classification type results. So you can't say every normal subgroup is finite or finite index, but you should be able to say every normal subgroup is of this type, and I think it should be still true that you can say that every representation of a von Neumann algebra, maybe you can say is one of these types. I can imagine some sort of theorem like that, but I don't actually know. Nobody's looked at that, or nobody's proven something like that.
Oh, okay, that's good. Thank you.
Are there any other comments?
Well, is there any conjectures that haven't been solved yet?
Yes, so of course, so lattices, even for irreducible lattices in SL2R, direct product SL2R. So operator algebraic superrigidity is still open for those lattices, although many sort of algebraic lattices we can do. So I have some joint work with Andreas Thom where we did this, but for lattices in general, we don't know. The other thing is, so this was one of two of Connes' conjectures, and this was maybe the less famous one. The more famous one is his superrigidity conjecture for property T groups, where he conjectured that if the von Neumann algebras of two property T groups are isomorphic, then the group should be isomorphic. And that's also an active area of research, but it has a different flavor from what I've discussed today.
Well, thank you very much, Jesse. We look forward to hearing some other new results and having you back again. So,
all right,
it was wonderful
thank
talk.
you for letting me be here.
Yeah. So bye-bye. See you again next week. Bye-bye.
Thank you.